The subject of this video is how to use the autoShim script to locate the proton Larmor frequency for your picoSpin 45 NMR spectrometer. A written description of the information contained in this video can be found in the Quick Start section of the picoSpin 45 user manual under the heading Finding the Signal, and in the Quick Start guide in the section titled Automatic Shimming. These documents are located under the documentation section of the support page of our website at www.picoSpin.com. Both HTML and PDF versions of the documentation are available. We will cover topics such as how to adjust the transmit frequency, the bandwidth and post-filter attenuation, the maximum number of points to plot, the maximum time to plot, and also how to size the spectrum window. First, we need to navigate to the autoShim script. This script can be found on the Run page. If you're not already on the Run page, simply select Run in the upper right-hand corner of the user interface. This will refresh the screen and take you to the last script that you were using. If this isn't the autoShim script, then navigate over to the Scripts button and select it. A pop-up window will appear and you will have 3 factory default scripts to choose from: autoShim, OnePulse, and Search. And we want to select the autoShim script. Next, we want to make sure the test run box is checked. This will allow us to execute a single RF pulse when we start the script. Simply check the test run box if it isn't already checked. Now execute the autoShim script by clicking on the Start Run button. What this will do is give us an FID plot and a spectrum plot to look at. You can see that in the FID plot on the top and the Fourier transform spectrum window on the bottom that there is no signal, we just see noise. What we want to do is discover the transmit frequency necessary to generate an NMR spectrum, but the bandwidth and our spectrum frequency window are too small. So let's open up the bandwidth. We need to make it larger so we can look at a larger window, and then we'll make adjustments from there. I'm going to navigate down to the bandwidth parameter and change it from 4 kHz to 64 kHz. I'll also need to change the post-filter attenuation parameter, which is basically a gain control for the bandwidth we're using. In this case, with the 64 kHz bandwidth, I want to set the post-filter attenuation parameter to 6. Since we're working with 64 kHz of bandwidth, we can expand the width of our spectrum window to a maximum of plus or minus 32,000 Hz. I can accomplish this by changing the minimum frequency to plot to minus 32,000 Hz and the maximum frequency to plot to plus 32,000 Hz. Also, because we're collecting 1,000 points out of 64 kHz, we'll only need to acquire about 16 milliseconds of the FID time series. Right now we have 250 milliseconds in the max time to plot parameter field. So we'll change this to 16 milliseconds to reflect how much data we're going to acquire. Let's execute the autoShim script by clicking the Start Run button and take a look at what we have. You'll notice in the FID window we have about 16 milliseconds of the time series being displayed. And in the spectrum window below it we have a signal, but it's some distance away from the center frequency for the transmit frequency we've applied. We'll need to adjust the transmit frequency so that the signal is closer to 0 Hz. The process is simple. First, we need to take note of where the signal is located. Based on our spectrum, I would estimate the signal's position at approximately plus 4,000 Hz. I would need to adjust the transmit frequency by 4,000 Hz to bring it closer to the center frequency. What we need to do is add this value to the transmit frequency. If our signal appeared at minus 4,000 Hz, we would subtract 4,000 Hz from the transmit frequency. Before we do this, let's take a look at the transmit frequency itself. We need to take note of the transmit frequency units. We're working on the megahertz scale. If we look at the values in the TX frequency parameter field, starting from the leftmost digit, the first number is on the 10 megahertz scale. The second number is 1 megahertz. The first decimal place is 100 kilohertz, then 10 kilohertz, 1 kilohertz, 100 hertz, 10 hertz, and finally 1 Hz. When we want to adjust our frequency, we need to keep in mind which decimal place to change to shift the signal by the desired amount. For the current location of our peak, we want to adjust the transmit frequency by 4,000 Hz, and this means we need to add a 4 to the value at the third decimal place. If I add 4 to the value 6, I'll change 46 into 50, and my transmit frequency becomes 44.15017 MHz. Now I'll execute the autoShim script once again. You can see our peak shifted to the right and is closer to 0 Hz. And that's how we adjust our transmit frequency. We've done a pretty good job at placing our signal very near the center frequency. Once we zoom into the spectrum window by changing our bandwidth back to 4 kHz, we'll determine whether we need to make additional adjustments to the transmit frequency. I'll navigate to the bandwidth parameter and change 64 kHz back to 4 kHz. I'll also need to change the post-filter attenuation value from 6 to 10. Let's change the spectrum window minimum and maximum frequency to plot values from minus 32,000 Hz to minus 2,000 Hz, and from plus 32,000 Hz to plus 2,000 Hz. We also need to change the max time to plot from 16 milliseconds back to its default value of 250 milliseconds. We can leave the max points to plot at 1,000 points. Then we'll navigate up to the Start Run button, click it, and execute the autoShim script once more. You can see that when we zoom into a 4 kHz bandwidth, the signal which appeared to be on 0 Hz is slightly off resonance. Our signal is actually located at approximately minus 200 Hz. So that we can solidify our understanding of the process of adjusting the transmit frequency and its effect on signal position, let's make another adjustment to the transmit frequency. This time I'm going to push the signal from its current location on the negative frequency side of the spectrum window to a positive frequency. Let's place the signal so it appears near plus 500 Hz. This will require us to adjust our transmit frequency down by 700 Hz, this being the frequency difference between plus 500 and minus 200 Hz. I'll change our current value of 44.15017 MHz to 44.14967 MHz. Once again, I'll execute the autoShim script by clicking the Start Run button. You can see we made a pretty good choice on our transmit frequency, but I'm going to shift the transmit frequency a little more to the left by changing the fourth decimal from a value of 6 to 5. This will have the effect of shifting the transmit frequency an additional 100 Hz to the left. Then I'll execute the autoShim script once more. And that's how we use the autoShim script to discover the proton Larmor frequency of our picoSpin 45 NMR spectrometer. In this video we learned how to adjust the transmit frequency, the bandwidth and post-filter attenuation, the maximum number of points to plot, the maximum time to plot, and also how to size the spectrum window. Keep in mind that when changing the bandwidth, the post-filter attenuation parameter must also be adjusted, and that the number of points you acquire within that bandwidth determines the maximum time you can plot within the FID window. The minimum and maximum frequency of the spectrum window is also determined by the bandwidth. For example, given a 16 kHz bandwidth, the minimum and maximum frequency limits for the spectrum window are minus 8,000 and plus 8,000 Hz. You can, however, make the spectrum window smaller in order to zoom into a signal or a region of the spectrum by typing in the desired values into the min and max frequency to plot parameter fields. Now that we've adjusted the transmit frequency such that our signal is within plus or minus 500 Hz, we can move on to the next step of using the autoShim script to optimize the shim coil current values and shim our instrument. In our next video, we'll cover the subject of automatic shimming. There is a detailed description of the shimming process in the system maintenance section of the picoSpin 45 user manual under the heading titled Shimming. This documentation is located under the documentation section of the support page of our website at www.picoSpin.com. Both HTML and PDF versions of the documentation are available.